All right, I think we're ready to start. I just want to double check that everyone online can hear me.
Good morning,
Yes,
Professor.
All right, thank you. So today is our second day of week 3. So we're still talking about points of intersection, systems of equations. We'll be working with larger systems today, 3x3 systems, and a little more with some break-even points, some examples with that, or at least one example with that. I was hoping to get to a little preview of what we'll be doing next week, which is matrices, but with my other 2 sections, I didn't get there, so probably not with you guys either. Right. So some quick announcements. Obviously, our next day is a holiday, so Tuesday we'll make up with this, or make up for this with just a review day way later in week 16, right at the end of the term. So I'll tell you about that schedule later. So no class on Tuesday, so next class will be Thursday. Homework. Homework's been returned to you. I posted a thing with detailed comments and feedback on the classroom page that you guys have seen, or you can see. I have a list of some common mistakes that happen for each question. Like lots of people forgot to do this thing or made a mistake in this point or whatever. So you can look at that stuff to get some sense of where you might have lost points, although most people, this first homework was not too tough. Most people did pretty well on it. If you look at the general feedback and you're still not understanding where or why you lost points, then you can come talk to me or write me a message or something, and I can give more specific feedback there. But there were a lot of people who lost points for very avoidable things, like they just did the wrong questions completely. It's always the exercises part of the book. So in the back of each chapter section, there are examples with numbers and then the try it questions as well, but it's always the exercises. So please make sure you're doing the correct questions. Formatting, there were not too many people, but most people were fine with this, but some people had their work like rotated. One page was rotated this way, the other. Like, I'm not gonna sit like this for 2 hours while grading homework. Like, I'm not gonna like turn my laptop or something. Just, you need to submit your work correctly. So most of those cases, we just said, sorry, but we're not gonna look at this. It's too much work for us to fix those submissions for all those students. So those people just didn't get a grade this time. Please be careful more careful in the future, basically. For a number of people, we wrote specific comments like, okay, there's a mistake on this question or something. We don't always have time for that, but we'll try to do that when possible. And no resubmissions, sorry, but it's way too many people. You're able to check your answers before you submit. With most things with math, you can like take your final answer and recheck that with the original equations or whatever and make sure that it works. So you are able to check your own work. So we won't be accepting resubmissions. Yeah, so that's just general comments. There's more written on the classroom page. Anyone have questions beyond that? No. All right, then let's go to some review from last time. So we did these smaller 2x2 systems. So let's take a moment now. Please try to solve these. Substitution or elimination, it's your choice. Whatever seems more effective here. Go ahead. A reminder for people online, if you're finished, you can write your answers into the chat and compare with other students. All right, that's been 4 minutes, so we'll go ahead and take a look at these. The one on the left, what looks easier, substitution or elimination? Substitution, okay. I would agree. We have this, one of our variables is already isolated for us. So that's very convenient. We can make use of that. So we'll just take that y from equation 2, substitute that into equation 1, and x plus 2 times what y is equal to negative 0.5 x plus 5 10. And we just simplify x plus 10 equals 10. And we get this result. X's are disappearing here. How do we interpret this? Louder? What does this mean? Infinite number of solutions. So there are no constraints on our solution here, or the only constraints are just from one of the equations, but we have an infinite number of possibilities. If we're talking about just 2 lines in a 2-dimensional space, then that's a coincidence situation. But if your variables disappear, both sides are equal, then we have an unlimited number of solutions. All right, do the one on the right. So here, what does it look like is easier, substitution or elimination? Elimination. So we kind of have the variables lined up here. We just take the second one, switch that around. So if we do that, equation 2, 3x to 2.5y equals 2. Okay, and then 1 is the same. And then from that, what will we do to do the elimination? Okay, so equation 2 by 2. So equation 1 is the same. Multiply equation 2 by 2. So 2x minus 5y equals 7. And multiply this by 2. So 6x minus 5y equals 4. Are we adding or subtracting these two? Why subtracting? All right, so same sign here. Subtracting is what will make those go away. So we are subtracting. And that gives us negative 4x. For thoroughness here, we could write 0y just to make sure that we can confirm it does actually go away. And then simplify here, x will be equal to negative 3 over 4. All right, do we want to substitute our x value into the first equation or the second equation?
The first one.
Why the first one?
Because there is 4, that's the least common.
So we have a 4 on the bottom of our fraction here, and then we have a 2 in the coefficient. It's not going to get rid of the fraction, but it reduces it kind of nicely there. We have a common multiple, or common factor there. So then substitute that into equation 1, 2 times -3/4 minus 5y equals 7. And we just reduce and try to simplify here. So this will be, I'll write this as decimals here for convenience. This will be -1.5 minus 5y equals 7. So -5y equals 8.5. And then so -8.5 over 5. That's a pretty ugly looking fraction. How could we fix that a little bit?
Or if we make it 85 minus 85 over 10.
Okay, so over 10. So 10 on the bottom. And what would we have on the top?
85.
-17.
17. We're multiplying by 2 here. Okay. So then I've kind of run out of space, but our final solution here would be the point -3/4. Or we have a decimal. No, we have them both fractions. -3/4 and -17/10. Or as decimals, -0.75 and -1.7. So either way. Okay, so on the right, it's just a point. It's a single solution. So just one point of intersection between those two lines. And on the left, we have no constraints, so infinite number of solutions. So just some warm up there. A quick review of what we talked about last time. So substitution. So basic process isolates, then substitutes. It's working because we are assuming that there is a pair and we just try to figure it out. Then see what happens with our results. Elimination. Rearrange if needed, and then eliminates. And then from there, it's not too hard to just solve for whatever is left over. For elimination, what are the two operations that we can do?
Add and subtract.
Add and subtract what to what?
Two equations.
Okay, so we can add or subtract one equation from another equation. So that's the thing we spent a little bit of time talking about last class. We spent a bit of time talking about that last class, about why that works. And what is the other operation that we have for elimination?
Subtract.
Okay, so add, subtract, I'm just adding and subtracting is kind of the same thing. There's another different, wholly different kind of operation.
Multiplication and division.
Okay, so multiplying and dividing any equation by a constant. So multiply equation by a constant. So intuitively, we kind of know these two things and we know that we like to do them and how to do them. I'm drawing attention to them here because when we switch over to matrices in the next class, we'll see the connection between these two processes. So it's helpful to just kind of remember exactly what we're doing so we can recognize it in a new context. And then possibilities. If we get an impossible results, then that means that we have 0 solutions for that system. If we get just a unique solution, like here's the X, here's the Y value, That's just one solution. And if we get a situation where we have no constraints, so just the two sides are equal, there are no variables left over, then we have an infinite number of solutions. So 3 possibilities. All right, one more practice from last time, a break-even question. So similar to what we did last time, but just slightly different scenario. So you have some fixed costs and the other things here, trying to figure out what the, well, read the question and then see what it's asking you for. Go ahead. I see some people reaching for their phones. The calculations on this question are not hard. Should be quite easy to do just in your head, if not on paper. All right, let's check this one out, see if we can figure this out. Okay, so first let's make sure we understand the question here. What is the minimum number of sales needed to ensure the company does not lose money? What is that asking us for? Okay, so that's exactly what the break-even point is. So the point where you are no longer losing money. If we're over that point, sure, that's fine. But it's asking what's the minimum number to not lose money. That's the same thing as having exactly zero profit. That's the break-even point. Okay, so how are we going to find that?
Shall we find the total cost?
Okay, so let's start with the total costs.
Yeah.
What is
It
our
is
total cost for this?
fixed variable cost plus fixed cost.
Okay, so variable cost plus fixed cost. Variable costs here are
15Q
15 euros times Q
plus
plus
1,000 euros.
1,000 for our fixed costs here. So
Yeah.
remember, so fixed costs, that's the 1,000, and then cost
Revenue
to
is
produce. 1 second, please. So cost to produce. So remember, that's the cost. It's not cost to consumer, it's production cost. right, so there's our total cost equation. And our second thing, what do we need?
We have to find the revenue.
All right, so CR,
Okay, 35 euros. Like,
so 35Q, that's our total revenue. All right, so all right, so lots of people at this stage would just jump to, well, I know that TR equals TC and then figure it out from there. Is total revenue always equal to total cost? No, just only at this very one special point we call the break-even point. So this will work for the break-even point, but some people get confused and think that this is always true. It's not. So let's think a little more generally in terms of our profit equation. I'll write that here. So if we made our profit equation, it would be
minus
minus 15 to 1,000, and that's 20 Q minus 1,000. And then from here, we're saying, okay, that's the basic profit equation for this situation. And we want the point where profit is equal to 0. So that means that we'd have this case 0 is equal to 20Q minus 1,000. So we just solve for Q here. Not very hard. Q is what? Actually, let's just make sure. 50.
50.
So, right. So minimum number to not lose money, not lose money. There was very careful wording there. So 50. I saw some people in the chat wrote 500. Just make sure we get the zeros right with our division there. Sorry? 1,000 divided by 20. So if we just had the TR equals TC, we could have jumped straight to this pretty quickly. But if we understand it this way, then I could ask you a different question. Well, what Q value will give us a profit of, say, 1,000 euros? If they want at least that much profit, what Q value will give them that? And then you could just substitute that value in here. But if you just say, well, TR is always equal to TC, then that gets a little more confusing here. So kind of take one step back and just think a little more generally, and then we'll be able to have a better understanding of these kinds of situations. Okay, so practice, let's go on. So now back to our kind of intersections, the new thing for today. Last time we had this equation, this system of equations, the two equations, two unknowns. Remember, unknowns just means variables when we talk about this. So now we'll look at slightly larger situations like this, 3 equations and 3 unknowns. Just to remind everyone, I'm sure we remember, but if we have 3 variables and we're going to find a single solution for that system, then we need at least 3 equations. If we have 3 variables, but only 2 equations, that's just not enough data points. There will never be a single solution. So if we had 4 variables, we'd need at least 4 equations. So 5 variables, 5 equations like that. At least needs to equal the number of variables you have. All right, so we'll go through this one here with substitution ends, then again, the same one with elimination. And we'll just kind of see what the process looks like for a larger system like this. All right, so solving with substitution, we're doing the same thing as before. We'll isolate one variable, and we are going to substitute that into other equations. And then the result will be a 2x2 system. And then we do our process for solving the 2x2 system, and then we get down to solving one variable. Okay, so if we start here, substitution, we have a few different choices, or like the easiest ways to do this. Variables that have no coefficients, that would be nice to work with. So we could kind of do any one of those. Does anyone have a preference?
The third one.
Saying x. Okay,
Yeah.
so third equation. We'll use x. All right, so isolates. 3. X will be equal to -2y minus 4z minus 1. All right, and we will substitute into say equation 1 first. So equation 1 will become 2 times this thing, -2y minus 4z minus 1 plus y plus 2z equals 4, and expand and simplify. -4y minus 8z minus 2y plus 2z equals 4, and then -3y and minus 6z will equal 6. All right, and we notice here we have a common factor of 3. So we would probably want to take that out here and rewrite this as y plus 2z equals -2. Common factor of -3. All right, this seems like a pretty useful result, so we'll call that equation 4. Give it a label there. What do we do next?
Do we use the elimination or substitution again in order to solve?
Okay, we do need to do more substitution. Let's think. Let's say if we took this thing and we move the z over, we isolate for y, and then we sub this y into, I don't know, into this equation. What would happen? It would work? Why not? Okay, so someone else is saying it won't work. Why not? All right, so we still have an x here. So we got rid of the x, but then we'd just be bringing it back. So we are going to eventually try to solve for y and z there, but what do we need to do before that?
We have to resubstitute the x
Into what?
into the left part of the equation.
The left part?
I mean,
Okay.
into another equation.
There we go. So we substituted x into equation 1 here, but we also have equation 2. So you need to substitute that thing into each other equation. We need, here we have 2 variables, y and z. If we're going to solve for 2 variables, we need 2 equations. So we need 2 equations with y and z. We don't have that yet. We have to make that. Then we can eliminate there and solve it. So let's do that. I might run out of room here. We'll try to write smaller. So take our x and we are going to substitute that into equation 2 as well. So that's 3 times what we said x is equal to negative 2y minus 4z minus 1 plus z equals 2 plus y, and then expand and simplify. Negative 6y 12z minus 3 y. All right, our y terms, looks like we have a negative 7y and 11z and 11z and then equals 5. You can see there's a lot of little arithmetic happening here. Easy to make a mistake with the signs or something. If you do notice me making a mistake here, please let me know. That looks right. Let's see. Okay, so then we will label this one equation 5. Okay. So we have 2 equations now with just 2 variables in them, y and z. So now we do our method for solving a 2x2 system. We're just kind of peeled off one layer. Now we repeat the whole process again to simplify down to just one variable. All right, so 4, it looks like it's pretty easy to isolate for y in equation 4 here. So let's do that. I know this is not super organized, just because I'm running out of space here. So page 4, and we would rewrite that as y equals negative 2z minus 2. And we'll substitute this into equation 5. So 5 negative 7 times negative 2z2 minus 11z equals 5. So negative 14. Oh. Positive 14z plus 14 minus 11z equals 5, and 3z is equal to, looks like negative 9, z is equal to negative 3. So that looks like a very useful result. We've actually solved for one of the variables. So let's give that a label. We'll call that equation 6. All right, so from this point, hopefully it's pretty clear. We will take equation 6, and what's next?
Substitute again.
Okay, so we substitute. We'll go back into, we could do equation 5 or equation 4. Equation 4 looks a lot easier. So we'll do that. Equation z into equation 4. So that gives us y is equal to, sorry, y plus 2 times negative 3 is equal to negative 2. So then y will be equal to 4. All right, we solve for 2 of the variables. We could even give this one a label as well. Equation 7. And then we take our y and our z and we go back into any one of the original equations and figure out what our x would be. I'm going to write over here. So we take our y and our z. Which of the original 3 equations would you choose here? 1, 2, or 3?
The third one.
third one. Yeah, we have the x is isolated here. It doesn't really matter. None of these are too complicated, but we can do that one. So into equation 3. So x plus 2 times 4 plus 4 times -3 is plus 1 equals 0. All right, so x plus 8 minus 12 plus 1 equals 0. So that means x is equal to 3. All right, looks like finally we have our full solution, 3, 4, -3. If we want to check, just like we talked about before, we substitute these values into each original equation, make sure that they all work out, and then we can confirm. I will skip that process here. So just checking our answers is not too hard. But substitution, it gets a lot bigger. If you can imagine, if we were trying to do this with a 4x4 system, we would need a lot more paper or a lot more screens here. So it can get kind of messy or long like this. So let's, or does anyone have questions about what we did here? So we take our 3x3 system, make a 2x2 system, and then just repeat. So we could scale this up infinitely. It just starts taking a really long time. All right, we'll do this again. I'll give us a little shortcut here, and just if we do this and we target the y instead, things are going to work out a little more nicely and a little more quickly. But we'll do this with elimination as well here. So elimination is going to be the same kind of idea. We have to make 2 new equations that have reduced one of the variables, and then that will make a 2x2 system, and then eliminate again to get down to one of the variables. Okay, so let's say we are going to use y in equation 1 here and eliminate and get our 2 new equations. So let's say we're going to use equation 1 and equation 2. Do I need to, and my goal is to eliminate the y. Do I need to multiply by anything?
No, we just have to add.
Right, we have the same coefficients on both. No multiplying is necessary. We have opposite signs, so we're just going to add them, and then we will eliminate the y's. So 2x plus y plus 2z equals 4, and 3x minus y plus z equals 2. Adding. Five x plus 3z equals 6. That's one of them. And we'll do this again. We'll do this again with equations 1 and equation 3. So what do we have to do in this case?
We have to multiply the first equation by 2.
First equation by 2, and we are adding or subtracting.
And then we just subtract.
We are subtracting because we will have the same sign on both of our variables. So, sorry, both of our coefficients. 2x, not 2x, you're multiplying by 2. So 4x plus 2y plus 4z equals 8. And the other one, we are not multiplying. X plus 2y plus 4z equals -1. And we might notice something very convenient happening here. So 4x minus x is 3x. And then 2y subtract, so 0y. But then also,
Zero is that.
conveniently, the z's are canceling out as well. And then here we get 9 and simplify, x is equal to 3. So we got really lucky here. Normally we would get a new equation. So we would call this one equation 4, and then we would get some new equation 5 that has 2 variables, and then we have 2 equations, 2 unknowns. We do the elimination process again to solve for one of the variables, but we just found this little shortcut in this, and by chance it worked out like this. That won't always happen, but sometimes, so that can happen. All right, so x is equal to 3. Then we'll just take that and substitute back into all the other ones and solve that way. So let's take our x is equal to 3, and we can substitute that into equation 4. So x into equation 4. So 5 times 3 plus 3 z equals 6. 3 z equals 6. And we simplify that, we'll find out that z is equal to -3. And then take both of those, go back into one of the first equations. I'll just skip that for sake of time, dot, dot, dot. We'll realize that y is equal to 4, same as we found before, and then there is our solution. So the difference with elimination and substitution is what we do getting down to solving for one of the variables. But after we solve for one of the variables, we're just substituting back into the previous equations that we had. So kind of on the going backward part, substitution and elimination are the exact same process here. We're actually just doing substitution going back. It's just a difference of getting to this point. When we do our matrices stuff in the next class, we'll actually see how we can do elimination going back up as well, but we haven't done that yet. And that's not something that people typically do when they do elimination like this. So larger systems, 3 like this, or if we had a 4x4 system or something, you can just kind of see how it would be a lot more work and not very fun to do. But we'll see when we use matrices that we can have a way that we can do this a lot faster. We'll do the same number of calculations, but we can actually do many at the same time, and there's a lot less writing involved. So that will be a slightly more convenient way of doing elimination. So that's something we'll get to later. So for today, the next thing I want to look at here is a practice question for something. So take a moment to read this question and then tell me what tool or what method would be the most efficient thing to solve this. All right, so today so far we've talked about using the cost cross revenue profit equations, and we have also talked about using systems of equations. Which method, which tool fits this scenario? Why? Okay, so not because of the two goals. Explain a little more. It's not because of the 3,000 and the 4,000 having two different goals. Okay, so we have two different products basically. So those other equations we looked at for total cost, total revenue, is just Q, it's just one thing. Here, this is basically an optimization problem. If we make more of one thing, we have to make less of the other thing. What's the right kind of balance? The codependency. So those basic revenue profit equations we looked at are just for looking at a single product. This is a whole different type of problem optimization. We'll do more with this a bit later, but for today, we'll just kind of see how we can handle this with systems of equations. All right, so first thing we need to do is, this looks like two variables happening, but we need to very clearly define our variables. So let's say we're going to use X and Y. What can X be here?
75.
Not the number, and it won't be a number, it's a variable.
Okay, laptop. And price, a profit for laptop.
Not profit for laptops.
Quantity.
We have to be very specific. What quantity of laptops? It's a variable, so it's not a number. We want to define the concept. So number of laptops, what?
Sold.
Sold. Okay, so we have to be very specific with our variables here. So X will represent number of laptops sold, and then what can Y represent? Okay,
Number of phones sold.
Number of phones sold. So we don't actually have costs here. We don't have revenue. We haven't been given that information. All we've been given is profit. So we can't talk about number of laptops, like broken laptops purchased in order to repair, or number of laptops repaired. We can only talk about number sold because that's the only data that we have available here. So we have to be quite specific when we're defining these. All right, so we have two variables. So now we need to make two equations. So what's one of the equations we can make here?
X plus Y equals 50.
Okay, X plus Y equals 50. Why that? Where is that coming from? Okay, so
She has to sell most 50.
can only sell at most 50. If we were being really careful with this, we wouldn't say equals, we would say less than or equals, but that actually turns this into a harder version of the problem. We'll use a tool called linear programming to solve that in 2 weeks, but for now, we'll just pretend it's equal. We'll just kind of look at a simpler scenario. All right, so X plus Y equals 50, and we need another equation.
75X plus 50Y equals 3,000.
50Y equals, for the first goal here, 3,000. So some people were first saying, well, X is equal to 75. It's not that. 75 is the coefficient on the X. They're connected, but it's not the actual X value here. All right, so two equations, two unknowns. This now looks like a solvable problem. So What do we want to do? Substitution or elimination? Everyone's saying
Elimination, I think.
Okay. All right. So we'll take equation 1, equation 2. What are we going to do for elimination? Okay, so there's a lot of choices here. So multiplying the first one by 50 will work. We can also see that the second equation, we have a common factor of 25, so we could divide that by a whole bunch, but we would still be left with a 3x and a 2y, so we'd still have to multiply the first one by something anyways. So there's a way to do it with a little less work, then let's do that. So equation 2, 75x plus 50y equals 3000, and then we'll take equation 1. And we're multiplying by 50, so that means we're eliminating the y here. So 50x plus 50y equals, and on the right we'll have 2500. Right? Are we okay? So we're subtracting these two, same sign with the 50 here. So minus here, and 25x is equal to 500. So x is equal to 20. All right, and we probably don't even need to write out like, you know, the steps to calculate what y is. We can just kind of see it from this. Well, if x plus y is 50, x is 20, then y is going to be equal to 30. Okay, so elimination with this tells us that x would be 20 and y would be 30. How do we interpret this? Is this goal of 30,000, 3,000 profit, is that possible?
Yes, it is.
It's possible. So, and it's possible exactly when we do 20 laptops and 30 phones. So yes, it's possible, and this is exactly how we would do it. Let's do this again for the second goal of 4,000 profits. So I'll just kind of jump straight to this step here. We would get, okay, I'll write this out. So 75x plus 50y, but this will be equal to 4,000. Equation 1 is still 50, and 2,500. We're subtracting, still 25x over here. But now on the right, we'll have 1,500. So what is our x value?
60.
X value is 60. And then what would our y value have to be?
Negative 10. That's impossible.
Y would be equal to negative 10. Okay, so impossible seems like for two reasons. Or sorry, you tell me, why do you think this is not possible? Okay, so for both of these, both variable values here are telling us that this doesn't work. The x value, we would have to sell 60 laptops to make that much profit. And our problem, our scenario here is telling us that's not possible. The student just doesn't have enough time to sell that many things. Also, the second variable saying we'd have to sell negative 10 phones. Selling negative 10 things doesn't make sense. Like, that's not physically possible. So that also, just in the context of this problem, like we said, we have these two equations. Equation 1 is this, equation 2 is this. But we also intuitively know, sort of like little secret extra equations here. X must be greater than or equal to 0. X can't be negative, it doesn't make sense. Also, Y must be greater than or equal to 0 because other values don't make sense in the real world context of the problem. So we have kind of a violation there. So can't have negative values, can't be over 50. So the secondary goal is not possible. What we have not answered here is what is the highest profit? 3,000 is possible, 4,000 is not possible. So is 3,000 the highest, or is there some other number between the two? Yeah, this problem is not all that complicated. So you guys are probably just seeing, okay, yeah, more money for laptops, so just do all laptops and then we'll get some value there. But more formally, we can have a system where we have multiple trade-offs, not just one. And then we have to kind of balance and find what's the overall profit. So the simpler form of those with straight lines is called linear programming. That's our topic for 2 weeks from now. And then the more complicated one with non-linear lines, that is called constrained optimization, which is, we actually need a whole bunch of calculus tools to do that. That's going to happen in your economics classes later. So it is nice to be able to figure out what exactly the maximum is, and we'll see a simpler version of how to do that in a few weeks. But for now, we can at least say, well, you give me what profit you want, and then I can check that particular one and see if it's possible or not. So it's not as powerful, but we can get an answer out of this. Wow, we got here 10 minutes faster than my other 2 classes. I don't know why that, but that always happens with this section. We go a lot faster. So we actually have time to preview this, but the other classes didn't see it, so I'd have to repeat this in the other classes anyways. All right. I'll just give a quick verbal preview of this. We won't actually go through the practice questions that I have set up, but I'll repeat this explanation in our next class as well for the other students. Okay, so matrix. Not everyone, or probably a lot of people, don't really do this in their high school math classes. It depends on what kind of classes you took or whatever. But a matrix is this thing. It might look fancy, but it's just numbers in a box. That's all we do. We just kind of line them up in a grid. So yeah, you're right. I wrote it there and then I'm okay. That's right. I'll fix that later. So okay, so the numbers are supposed to be all equal here. So the system on the left is just represented by the thing on the right. So we can just see that basically we were lazy. We didn't want to rewrite all the variable names every time. So we just didn't write them. But then how do we know which number matches which variable? We just line everything up. So we can see here, it's all kind of a bit messy. The Z's are kind of not all perfectly straight. But then here, okay, so that's the Z column. And then the Y, the X, the W. Like this. They all just kind of line up. So that's how we can read our variable values. And then the right side, the constants, that's here. So we can just see how those line up. And then also each of the equations, we have an equation 1, 2, 3, 4. And we can just see, okay, well, that's equation 1 there, equation 2, 3, and 4. So there are lots of things that we can do with matrices. We're actually going to talk about them 2 times. The first time we'll just be doing elimination, but with these matrices, and we'll see how we can do a bunch of steps at once and kind of save a bit of time. The other thing that we will do with them, we'll do some other stuff, then we'll come back to them, is sort of a completely different way of thinking about them that is a bit more widely used. So we'll come back to that stuff later. But for now, this is the basic idea. Yeah. I'm not going to go through these. Come back to them in our next class and that as well. Okay, so the preview question that I have for next week, which I'm still going to make it due Sunday by 8 p.m., same as the previous ones, just for consistency. But I know we're getting close to a very long weekend, so you probably don't want to do homework in the middle of the weekend, so just do it today or tomorrow or something. Get it done early. So the preview question, the thing on the left, this matrix is equivalent to this system of equations on the right. If we solved this system of equations and figure out what x and y and z are, and then we try to write that solution as a matrix like this, but some of the numbers are going to be a bit different, what would it look like? What would those different numbers be if we solved x, y, z and put that in here? What else? Right. So there's some review questions in our book. If you want to get some practice solving these larger systems, 3x3 systems, there are a whole bunch of questions here. If you want some practice with word problems and taking some real world scenario, turning that into math and solving it, there's a whole bunch here in chapter 4.3 that you can work through. And I think that's everything. So next time we'll do a whole bunch with these matrices and row elimination and see how we can use this tool. All right, we are finished very early. All right, you're welcome. Goodbye. See you on Thursday next week.